Hi, so now we're going to talk about fractional slot windings and why they're useful, and why they've got problems as well. What is a fractional slot winding? You can have, so we've looked at the slots per pole per phase before. So the fractional slot winding means that you have slots per pole per phase that is not an integer. It could be less than 1, can be more than 1. So we're first going to look at fractional slot windings that are more than 1, having slots per pole per phase that are more than 1. So we're going to look at for Q greater than 1 first. So having an increased number of slots per pole per phase, Q, improves the field. So we saw this, if we had 2 slots per pole per phase, we definitely got a better waveform than 1. But if we, but an increase in Q, the slots per pole per phase, means an increase number of slots. So, but now if you think about a machine with a certain diameter, you're going to be limited by how many slots you can fit within that machine. So number of slots is limited by geometry, because the narrower slots, so narrow slots will become saturated. So what can we do? So it would be nice if we could have more than Q equals 1. So a fractional slot winding machine can allow you to have a machine greater than 1. For the strange machines we've been looking at with magnetic gearing, fractional slot winding is also useful because they can allow you to have choose a different number of stator slots that will not create unwanted harmonics, because the number of slots you choose will result in a particular harmonic being created due to those slots, that saliency. If you choose a slot number that is different to the fields that you're trying to interact with, that can be good, because the stator slotting will not necessarily cause torque problems, ripple, things like that. So fractional slot windings allows you to widen the number of slot choices that you can use, and you can find other designs that can create better results. Because remember, the stator field from the stator may create, say, 7-pole pairs, but the stator slots, they can be a different number of. You can have a completely different number that's not necessarily related to the pole pair number by an integer. That's what fractional slot design allows you to do. So let's give. I'm gonna, in order to explain how design a fractional slot winding with slots per pole per phase more than one, I'm going to just start by using an example. So the fractional slot windings, while not being a multiple of the number of poles, must be a multiple of the number of phases. This is important because we want to create phase symmetry. So for example, so we need to keep this in mind. So let's give now an example. Consider a 10-pole machine. So if we have 3 phases, then machine must have at least 30 slots to maintain phase symmetry. Right, because 30 times 10. So that would then give Q equals 1. 30 slots divided by 3 phases times 10 poles gives 1. So now let's say, so now if we had for slots per pole per phase of 2, we have Q equals 2. That means that this would need, we would need 60 slots, right? Because 60 divided by 3 times 10. Gives the Q. So, but we may not be able to have 60 slots. It's just not physically possible to put 60 slots in that machine. But we don't want 30 because it might create too many harmonics. So one possibility is to pick something in between. So for example, if we pick 42 slots, now there's a whole theory behind how many slots to choose, and they can go into more depth, but I'm just going to look at this case as an example. So in this case, if we had 42 slots, what would we have? So the slots per pole per phase, then we would have 42 slots divided by 3 phases and 10 poles. So that would then give us 7/5 slots per pole per phase. Now then, the slots per pole would then be 7 over 5 times 3. This 42 slots was chosen to make sure that we have phase symmetry, by the way. Can divide by 3. So 7 over 5 times 3 gives 21 over 5 slots per pole. So 21 slots have, so a way of thinking of this is that 5 poles has to be created using 21 slots. And then, but we have 42 slots, so after 21, the pattern repeats. So we need to fit 5 poles in 21 slots. That's what that's saying. So let me write that. This indicates that 5 poles must be distributed over 21 slots, and winding pattern will repeat. After 5 poles are wound. Okay? Now, the fact that we have 7 slots per pole per phase, that means that so the fact that we have 7 slots per pole per phase, that means that in 7 slots we have to have 5 poles occupying those slots. How do we do that? How do we enable, how do we have 7 slots with 7 over 5 slots per pole per phase? How do we do that? So one way of doing that is, so let me write this. So the fact that Q equals 7 over 5 implies that a slot occupied by one of the phases must alternate between 2 and 1 slot per pole. So again, we can't, thinking about it from what we've done before, you either have 2 slots per pole per phase or 1 slot per pole per phase? How can you have a fractional slot per pole per phase? So one way of doing that would be, for example, in our case, we could have 2 slots per pole per phase for one of the poles, and then 2 slots per pole per phase. 2 poles could be 1 slot per pole per phase, 1 slot would be 2, and then 1 would be 1 slot per pole per phase. If we did that and added it up, that would give us 7. There's another option is 1 1 2 2 1. So the first 2 poles are created with 1 slot per pole per phase. The next 2 poles are created with 2 and then 1. That would also give us 7. So, but what's the best winding arrangement? So it turns out that there's a nice way of figuring out the most symmetric way of arranging the windings, and that is by using star slots. So I'll talk about that, but before I talk about that, let's just talk about the pitch of the winding. So, pitch of winding. So let's think about this now, because we have this fractional slot winding. So what is the phase shift going to be? Electrical phase shift between the slots. So electrical phase shift between slots. So we have 10 poles. And each pole is 180 electrical degrees. And we have 42 slots. Right? So that's the electrical, and that's the that's electrical degrees, and that's the number of slots. So we have 10 times 180 divided by 42. That gives 42 and 6/7. So that's the electrical degrees divided by the slots. Electrical degrees per slot. Now, but we want to try to create a field that makes 180 electrical degrees for the pole. So we definitely would like more than 42 and 6/7 for the field to be created across. So let's see what the best option is. How many slots should we span across for the winding or the coil pitch? So coil pitch. So we have so if we choose If we choose 3 slots, that would then give us, so we multiply this by 3. That will tell us how many electrical degrees we'll have across 3 slots. So 3 times 42 6/7, that gives 128.57 degrees. 4 slots. That will give 171.43 degrees. And 5 slots, that will give 214.29 degrees. So the question is, which one is closest to 180? Because we'd like 180 degrees. That would be ideal. That would then mean that the pole pitch was equal to the coil pitch. Remember? So this would be the coil pitch. That's the W we talked about before, and this is the pole pitch. That's 180. We want the coil pitch to be as close as possible to 180. So this one, 171 is closest to 180, right? So we're going to choose 4 slots for to span. So like that, okay? So in this case then we could calculate the pitch factor Kp. That would give pi over 2 W over Tp. That gives where we have didn't put the sign in there, Kp sine. That gives us, so we have sine pi over 2, W is 171.43 and Tp is 180, so that gives 0.977. So that's pretty good. It's not going to give us too big a problem. Okay. So now how do we actually I should mention so then because the coil pitch is less than the pole pitch, it's called short pitched. Maybe I should just write that. So we can say that the coil is short pitched by 180 degrees minus 4 times 42/6 divided by 2. Divide by 2 because it's about 2 sides. So we'd so it's equal to is that right? Equal to right, 4 2/7 degrees. Yeah, that makes sense. Degrees, which is equal to 60/7. So it's short pitched by just over 4 degrees. Okay, so how do we? So we've decided on the number of slots being 4 that the winding will be spread over. So now the question is, how do we choose the winding pattern? Now, since we know that after 21 slots, the winding pattern repeats. So we only need to study this for 21 slots. So since winding pattern repeats after 21 slots need to sketch only first 21 slots. So how are we going to do this? What we're going to do in order to do this, we're going to draw a phasor diagram and use a concept called star of slots. And so I'll just briefly explain what the star of slots means. So let me say we can make a phasor diagram of the electrical position of the coils using a star of slots approach. Okay, so I just want to just explain physically how you can think of this, what the star of slots are, because it seems a little bit odd when you first see it. So we 7.2 star of slots. Okay, so star of slots. Meaning behind star of slots. Okay, so this is just a little digression. So consider a two-pole, three-phase, one slot per pole per phase winding. Okay. Now let me try to draw this. Oh. So we have minus A plus B minus C plus A minus B plus C, like that. Okay? So this is that's the slot pitch, and since it's only two poles, then the coil pitches 180 degrees, electrical and mechanical. Okay, so then now if you think about it, remember there'd be some rotor in there. So if you look at the A phase winding, so if you use the right hand rule, going to have flux. Whoops, I did that the wrong way. That's no good. That's not going to help. So we got the flux. We could going up So that's A. But then if we look at the B and the C, so the C looks like this, right? You can see these are here, so it's going to create a field going down like that, and then the B is 120 shifted like that. Like that, okay? So we could then put those three flux vectors together. So putting together on a plot. So we have A, C, B, like so. Then we can note that if E is equal to the change in your flux linkage with respect to time, if the flux linkage is given by this negative, then E would equal J omega times the flux linkage. So the induced voltage is always trying to oppose the change in flux with time, so that the voltage would be phase shifted by 90 degrees with respect to the flux. So then looking at this flux here, we shift this by 90 degrees for each of them, and then we'll have EA, EB, EC. Right? Now if we go back and look at our winding here, we have EB here. So this can be thought of as a vector coming out. Same with this. Same with this. So these can be thought of as the directions of the voltage. They correspond to the location of the slot. So directions line up with slot. So we can then instead draw up a diagram where we have voltage vectors coming off from the slots if they're positive, and if it's negative, going in the opposite direction. Okay, so let's use, and this concept is called the star of slots. So the star of slots vector directions correspond to winding position in electrical frame. So they represent the voltages. Okay? So with this, then we can utilize the start-stops concept to help us design the fractional slot winding. So in order to do that, I'm going to show a handout. I'll give showing some handouts which I will post, and we can then use those to draw out the star slots design. And let me just say one more thing before I show the handout. We can treat the when doing the star slots, we have to start somewhere. So we can treat the first coil as being at an angle of 0. So this will make sense when I show the picture. So coil number 1 can be treated as a reference coil at theta equals 0 degrees. Now what do we have in our design? Remember, we don't have 60 degrees electrical. We have 42 and 6/7 degrees electrical between the slots. Remember, this is a two-pole machine. So two-pole machine is unique in that the electrical and the mechanical angles are the same. But in most machines, you're going to have more. A lot of machines, you're going to have more than 2 poles, and so you're going to have the electrical and mechanical are not going to be the same. So when you go from one slot to the next, in our design, we have 42 slots, right? 42 slots. So from one slot to the next, we found that it was 42 and 6/7 degrees. So then if we choose the slot, the coil number 1 to be at 0 degrees, that would mean that the next coil going into the next slot, that would have to be at electrical degrees of 42 and 6/7. The following slot, third slot, would be then 2 times 42 and 6/7, and so on. So I'll show you a drawing of this. But let me just write this. So the first coil can be treated at being at 0 degrees, and then coil 2 is phase shifted electrically by 42 and 6/7 degrees. So therefore we can make a phasor diagram of these positions. Okay, so just give me a minute and I'll show the handout. So now, if we look here, this is the star slots that I was discussing. So what I've done is I've printed this out. It's a lot easier to do this doing this on a computer. So number 1 means that it's in slot 1. That is located at 0 degrees. Okay? Then number 2, that is the arrow corresponding to the winding being in slot 2. So the angle from here to here is then going to be 42 and 6/7 degrees. Okay? Then slot 3, numbered here with a 3, that's going to be another between slot 2 and slot 3, that is another 42 and 6/7 degrees, electrical, not mechanical. And so we can then go around and put in for slot 4, 5, 6, 7. Each one of these is shifted by 42 and 6/7 electrical degrees. Then we get to 8, 9. Now after 9 it gets really interesting. Then we go back and we start repeating. So we've got 10, 11, and we keep going around 42 and 6/7 degrees all the way around till we've done all 21 slots. 21. We don't need to do more than 21 because remember, after 21 the winding pattern will repeat. Okay? So then, so now the question is, what do we do with that? We have to figure out a way of collecting these vectors into 3 phases. So we have 21 slots and 3 phases, right? So how do we collect this up? So what we can do is we can look at this in three different groups. So we can note that that for each phase winding we have to have a total of 120 degrees, right? So that would mean that and each of the phases, the phase A plus going in and phase A minus going out, they're not going to be right next to each other. They're going to be 100. You'd want them to be the field going in. You'd want to be then shifted as close as possible, 180 degrees across for the phase current going back out with respect to the current direction when I say out. So how can we do this? So we know that phase A should be spread over 120, phase B over 120, and phase C over 120 because we have 360 degrees. So so what I've done here in this drawing is I have grouped them. So what if we look at, let's start with the middle one here, A. So from this starting point here to here, this is an angle of 60 degrees. Okay, and then so then we add 180 onto this from the beginning point, and then we choose the second span over here to be also A phase, so that would be 60 degrees. Okay, and then similarly the B with respect to A, that we put at from 0 to minus 60, and then opposite span across here. Can you see that? And then C is the other the other slice of the pie. So let's just take the A part, and this. So we will say that from here to here is phase A plus, and then this is phase A minus. Okay? Now looking at that, then we could group the winding. So we can say that that in this region, so we have 21 slots. So we need 7 slots for each phase, no more, because it needs to be even. So we can look at these these vectors and decide which ones should be in A and B and C. So clearly, like 13 over here, it's nowhere near the regions that we've said as phase A. So that wouldn't be in phase A. But from from the 0 angle to the 60, we can see we have a 1, 18, 10, 2, and 9. Those are all within the phase A region. So we could define these slots as belonging to phase A. Okay. Now, but we need to have 7 because we have 21 slots. So that's only 5. So we need 2 more. So we go across to the other side. We can see that we have also a 14 and a 6. That would be associated with negative phase A. So the 15 is sort of on the boundary. We're not using that one. That would give us too many. So we're gonna also include 6 and 14 in phase A. If we then now go to phase B, we can look at phase B, and where this is B plus and this is B minus. And so then looking at the B plus, then we have 4, 21, 13, and 5. They're fully in the span of 60 degrees for B plus. But we need 7. So then we look over to the other side. So we only have 4 here. We look over to the other side, and we need 3 more. So 1 has already been decided that we'll take that for A. So therefore we need 3 more, so that would be 9, 17, and 8 just on the boundary. So these 3 would also be grouped into B. And then the remainder will be C. So that way we can then group them, and I've done that here. You see that? So for the A, there was 2 that were in the minus, A minus. So I've flipped the arrows and put them as a minus 6 and minus 14. With the B, there were 3 that were in the negative phase B. So I've flipped those, and that's now minus 9, minus 17, minus 8. Okay, and then the C is similar. So with that, then we can now start to try to understand what this means. So the best way to do that is to draw up the winding pattern. So if you look down here, I've conveniently put some nice plots on, so we can do that. There. Oops. Okay, so if we look at phase A, phase A has a 1 coming out. So then we can define up as positive. So 1 is out, and then 2 is out. So on this winding diagram here, I'm going to draw a line coming up as being associated with 1, and then 2 is also going up. So I can draw another going up like that. And then now, so we've got 1 and 2, and then the next one we have is 6 going down. So I'll draw that going down like that. Now what am I missing here? This is only showing the winding going in one direction, but remember, it has to return, and we have said that it would return after 4 slots, right? Because of we need it to be 4 slots to create the closest span of 180 degrees. So that would mean that we have 1, 2, 3, 4. So that would mean that it would be coming down in slot 5. Like that. So we'll have 1 going in, then it has to return down here, Now, and then slot 2, that will be returning down slot 6. But we also have, so that's the return. But we've also said that we have a slot 6 going negative as well. So we're going to have another one going into here. So then the next slot is slot 10. So that's going out. So we can draw that going out. Now I'll just draw a few more. So we've got 14 going down, and then 18 is going up, and then 19 is going up, and that's all we've got. Okay, so now we have to keep in mind that they're going to return. There has to be 4 slots, so we've got to have a return path for number 6. So that would come along like that, and then we need to have a connection for slot 14, like that. Oh, wait, no, that would be the other way, sorry. So that's coming out, right? And then this one has to be connected like this because it's 4 slots. And then this one is this one's coming out, so it's 1, 2, 3, 4. That will be going back down slot 22, and then 19 has to go back down 23. Like that. Okay. So after 23, then they're going to start to whoops, it wouldn't be that way. They're going to start to repeat. So, and these would be connected up at the bottom. Maybe you could have something like this here. This is just one example. It's not a pretty one. You know, and so on. So then this is phase A, and then phase B we could draw up similarly. So phase B, we look now at the star of slots drawing, and we can note we have the 5, the 4, so we start with 4. So 4 is going, I can't really put those two together, can I? Maybe I can pull this out a bit more. No, I'm not going to be able to. You've got the drawing for the phase star of slot. So with the 4, with phase B we have 4 going out, so that would be up. We have 5 going up. Then we have what's the next one? We have 8 going down. We have 9 going down. And we have 12 going up, and 13 going up, 17 going down, and 21 going up. Right, like that. So we can join these all up. So I'm just sketching these in. This one's a bit clearer perhaps. Okay, so here we've got the phase B, and you can now connect these up also, and that's not going to be pretty either. The way I'm not drawing it very neatly, but you can do that. Now the interesting thing here to look at though is, now look at phase A. Okay, these are these two windings here. That's creating a flux that you know, going in, and then so this would be creating one pole. This is creating another pole between 6 and 10. This one's creating a pole between 10 and 14, and so on. So you can see that we have 5 poles indeed being created, and the first pole has 2 slots per pole per phase, and the last pole has 2 slots per pole per phase. The other 3 have only 1 slot per pole per phase. If we look at the phase B, it's a different story. The first 2 slots, the first two poles, sorry, are creating 2 slots per pole per phase, and then after that it's 1 slot per pole per phase. And so that's how you get this fractional slot winding. And so next time we will I will draw up the full winding function for this, and that I think will be quite interesting. Okay, I'll stop there. Thanks.